So today I will talk about applications, and most of these applications are concerned with simplifying multisums. So what I did the preparation in the last two parts to prepare you for that. And I think it's the right time also to mention some other summation tools. So the difference ring, difference field approach I tried to indicate the last two parts. Here are some other techniques. So there's no claim of completeness. There are papers missing, I'm sure. These are those which inspired me, that I enjoyed reading. So here is first the Sister-Selene WZ method. It started very early, maybe it's 45. Herbert Wilf, Doron Zeilberger pushed it further. There's a holonomic system approach introduced by Doron Zeilberger and substantially pushed forward by Frederick, and also by Bruno Savi, but here his Gröbner basis approach really made it fast. And Christoph Guchan worked also on the holonomic summation approach and pushed it further. There are reduction-based methods. This is more recent, where you are inspired more from integration, where on the summand level you have proof certificates. I always said we can verify this, and sometimes you can ignore some of the heavy calculations for verifying things, and you get much faster to the recurrence that you really need. So that's also fascinating. And there's also, I consider it as an own approach, the generating function approach, which is also very interesting. One could consider it as a holonomic closure property toolbox, but I thought it deserves an own way how they did it, so I like this a lot. Okay, so there are other tools that might be also interesting. I will focus mostly also on these parts here. Okay, so I was involved in quite some applications, and I decided to focus on combinatorics, number theory, and particle physics. So here I will pick out some applications, and let's go to combinatorics first. Okay, and here are the ones that I like most, where I worked on. Recently I worked also on was very interesting to do things here, and I decided let's pick out one where I can illustrate once more best the tools that you have seen 2 days ago. So I want to show you the unfair permutations that I did together with Helmut Podinger and Stefan Wagner. That's the following problem. We are given n players. This is not the problem, this is the naive way. Player I chooses randomly a number. All are different, so you have n different numbers. The player with the highest number gets n dices as reward, and the player with the second highest number gets n minus 1 dices, and so on. The player with the lowest number gets only 1 dice. And if you write it down, player 1, 2, 3, and here you get the number of dices, you get a random permutation. Okay. Now we slightly make it unfair, the game. We say player I chooses randomly I numbers among 1 plus 2, so they're again different numbers. Each one chooses a different number, but now the ice player can take I numbers and takes the best one, the largest, so it's unfair. So the higher you are in the player, the more choices the person has to get the highest number. Okay, and this is an unfair permutation. And you can say the player I is smaller than J, but J beats I, so J gets the larger number. This is exactly an anti-inversion to win. Okay, and now you can ask what is the probability. That's also easy. So if I and J both choose different numbers, they are I plus J numbers, and player J gets J numbers to choose. So the chances are higher that he gets a higher number, and he precisely takes J numbers, the other player only I numbers. So this is the probability that player J will win. Okay. And when you are interested in the expected number of anti-inversions or the expected numbers where this happens that J beats I, well, then you sum over the probabilities and all these pairs, I smaller than J. That's expected value. For the fair permutations, it's easier then you have here just 1/2 because each player is equally likely to win, okay? And there are n times n minus 1 tuples, so it's n times n minus 1 divided by 2. This would be the fair permutation. This is the unfair permutation. And the question is, how does this sum simplify? And Stefan Wagner and Helmut Prodinger easily could simplify that sum. One could also do symbolic summation, and they get this value in terms of the harmonic numbers, which relates to, it's basically that asymptotic expansion. And the fair case, as I motivated, is that. So you see the unfair permutations shift to the right, okay? Okay, and they were also interested in the variance. And you get that expressions, okay? And now they approached me and said, no, we don't want to do this by hand anymore. And can you do this, okay? So let me go to the computer algebra system Mathématiques. We load in the packages. And here basically is exactly that expression, okay? I just copied it. And now let's try to simplify. This takes a while. So let's go back. It's currently running. So let's look, for instance, at one of these sums. How can we do this? I illustrated that already in my first part. Well, we look at that sum. It's a triple sum. We look at the innermost sum. We see the next summation quantifier is j. So we compute a recurrence in j. We solve the recurrence in j. We simplify the solutions, and then we try to find a combination. Doing that, it turns out that sum can be simplified to that sum, where now you see j is in the upper bound only and not anymore inside, whereas here you have j and j at different places. So it's an indefinite nested sum, so I can put it inside. And it fits again to my machinery. So this can be represented in a difference ring, how I like it. And I sum over j from 2 to k minus 2 by computing a recurrence in k, solving in k, finding the linear combinations, and then it turns out that sum here simplifies to that. And finally, I do the last round. I compute the recurrence, I solve it, I combine it. Okay, here's the solution, but let me go back. And we finally get that simplification. So in other words, this triple sum simplifies to that. In terms of the harmonic numbers, here are the broken harmonic numbers and also these versions here. And these sums here are all algebraic independent with respect to n, so I eliminated all algebraic relations as I motivated in part 2. But if you go now to that, I do this basically for that sum, I do it for that sum, that sum, that sum, and then all the different passes how I calculate, and the different sums that might arise. And there are still algebraic relations if I put it all together, so I have to compute again relations in the end to eliminate everything. And that's precisely what happened. So I did one of these sums, I do all the other sums, and I find in the end all relations and try to reduce as much as possible. And voila, that's the result in about 70 seconds, okay, that you get. And well, this is a language in Sigma coming from physics. Let me write it like that. If you prefer to see the sum versions, then these are exactly these broken sums here. And there are no relations among these objects, okay? So you cannot simplify further. And simplified in that basically, a bit nicer written down, is basically the variance. And you can do asymptotic expansions and can now extract certain properties, how it looks like. Okay, this was one example. Now I want to go to number theory, show you an example from number theory. There are, again, quite some things that we considered in the last years. Recently also, we looked at the error term of the partition function. That was very interesting for me because when Silvio Radu and Christophe Banerjee wanted to analyze the error term, this is connected also with Hadi Ramanujan, Wright, Rademacher, Lehmer, and others. And it turned out that in the analysis also multisums popped up and one had to simplify them, and only in the simplified versions that I gave them they succeeded in doing it. They said without that they couldn't do it. I don't want to say more things, but it's interesting that in this analysis of error terms, sums pop up and it's a need to simplify them. I want to look at that case. It's a case study of theta 4 that I did with Vadim Tudilin. So actually he contracted a problem. This was a long time ago, 2002 or 4, he showed it to me. And I thought, well, maybe I can do it. Then I stopped looking at it. And then finally he looked again, visited us at Risks 4 years ago. I said, now let's look again. When he comes, maybe I can show it to him. And then proudly I had something, I showed it to him and said, yeah, but I have a more complicated conjecture meanwhile. And what I did was only an initial value problem. So he showed me the real problem and it took me another 2 weeks. And I want to show you a little bit how this works. But before doing so, actually for that I need now the difference ring approach, but I also need the holonomic system approach. So it's a combined version, which I call somehow the holonomic difference ring approach, where I try to combine 2 worlds, okay? And I want to give you a little bit details on that, and that's also nice because then now you see a bit the holonomic summation machinery, okay? So let's look at that problem. It's a startup. Here are basically the Jacobi polynomials written in this PFQ form somehow. And I want to find a closed form. So let's first, same tactic, I try to work from inside to outside. Let's look at the inner sum. Okay. So I insert the Jacobi sum. Of course, in the database, this is an orthogonal polynomial. There are recurrences available. But since we have the summation tool, we can start from the summation representation and then compute the recurrence by basically, Zeilberger's algorithm. So here is the recurrence. You find it also in Abramowitz-Degun, and you find it in the digital library where currently also computer algebra section is written. Hopefully it comes soon in the NIST project. So we can compute these recurrences, okay? And now the problem is, what I find here is a recurrence of order 2 that I cannot solve in my difference ring world. I don't find indefinite nested sums and products. The recurrence somehow is the optimal way to represent it. I fail to find indefinite nested sum representation. So I cannot continue how I want to continue usually to solve the recurrence, combine the solutions, and then continue. This doesn't work here. So the idea also in the holonomic summation approaches, work with the recurrence instead of solving it. So I define the sum like that, where pk is now given, and there's a comment, sigma reduce, which I can extend saying use in addition the recurrence relation. If I do that, then I get a closed form, and I can express it just by pn plus 1, and the constants. Okay. So let me give you some more details how this works. Okay, so we want to find a closed form. I just make again the ansatz of telescoping. I look for a G such that this problem holds. Sigma computes GK in this form. If you don't trust, you can plug it in. You can note GK depends on this. GK plus 1 depends on PK plus 1 and PK plus 2. But PK plus 2 can be simplified to PK and PK plus 1. This is a holonomic idea. You have also seen it in Jacques Arthur's talk that you can always reduce. And using this relation, plugging it in, you can again, by polynomial arithmetic, verify the correctness on the summand level. Okay? It's just that I don't use a first order recurrence to use relations, it's a second order recurrence to use that. And summing this equation over k from 1 to n gives you the closed form. So let's go a bit more into details how this works. We have here our ansatz. As you have seen, I look for G0 and G1 such that this telescoping equation holds, and I just plug it in. Okay? Plug it in, similar what you have seen in the difference ring approach. Now I use the relation that pk plus 1 can be actually rewritten. It's like the verification. I do it also for my ansatz for solving. I plug it in, and then I get basically this expression here. I just rewrite it. Now, I want that basically these coefficients are 0. If these coefficients are 0, then basically the equation holds. Or in other words, if these two equations are satisfied, then the telescoping equation holds. This is a coupled system. And now the interesting thing is if you shift that and plug it in, you immediately get here a recurrence which depends only on G1, not on G0. So it's an uncoupled system. And that's exactly in the world that I also can solve. I can solve a linear difference equation which depends only in one unknown, a scalar equation. So it doesn't depend on G0, it just depends on G1. So I solve that, I get G1, that expression. And then if I have G1, I get G0 for free. I just plug in G1 and I get G0. So I get that. Okay? So that's the basic idea. And the interesting thing is, this is the same problem that I've shown you earlier, but now instead of a recurrence of order 2, I allow now a recurrence of order s. So here I have to shift s plus 1. So it's a higher order recurrence. Okay? And then this uncoupling can be done in one explicit formula. I don't have to uncouple by complicated or expensive algorithms. Given this problem, I can encode this scalar recurrence without uncoupling algorithms, which is good. It's fast. Okay? I don't need any complicated algorithms. So I solve for this equation, and then I get G0 if I know Gs, and then I get all the others by plugging in Gs and the values below. So it's just solving this equation, and everything is for free. Okay. You can generalize slightly. So this is the basic idea. And again, it reduces to solving an mth order difference equation, what I motivated in part 2. Okay. Now we can do a slight variation. Of course, the summand can also depend on pk plus 1, pk plus 2, and so on. Why not? Why should it only depend on pk? I'm a bit more flexible here, but we don't have to go higher than k plus s because we have the recurrence relation. All shifts which are larger, I can reduce by at most k plus 2 s. Okay, and then just the right-hand side slightly changes, but it's still a formula once and for all you implement, and you don't have to repeat things. And well, instead of one parameter, you can now use F0, F1, F2. You have several such guys. And then you have basically here a parameterized linear difference equation. So this is given, this is given. I'm looking for C0, C1 up to CD, and I look for the GS. This is exactly looking for a parameterized mth order linear difference equation. What I've motivated, it's popping up exactly at this point. So I solve this equation, find the constant C0 up to CD, and then compute the remaining things. And in this way, I solve the parameterized first order telescoping equation for my holonomic summation problem. No uncoupling is needed. And this is now the application for multi-summation where I'm interested in. Let's look, for instance, at that sum. I want to prove that double sum identity equals to that expression. So the idea is we compute for both sides the same recurrence. And then, well, we compute two recurrences. It turns out they are the same. So I only have to look, and it's of order 2. It's exactly that one. So I just need two initial values to verify. So let's look how this works. First, I compute a recurrence for that guy. Here I could use also Zeilberger's algorithm. I just use sigma. It's a special case. We get exactly the recurrence that I claim. You can also verify correctness by looking at the summand recurrence, but I ignore that. Now let's do the second part. I want to compute a recurrence for this. And I start again from inside to outside. I look first at the inner sum. Okay? And I compute the recurrence. That's the recurrence. And now, of course, I can try what I did earlier. I try telescoping. I fail. I cannot simplify by standard telescoping, what you have seen earlier, and sigma basically returns the sum itself. It's no simplification possible, okay? Now we do creative telescoping. We have still the parameter n involved, so let's use this shift in n in order to apply parameterized telescoping for creative telescoping. And in order to do so, I have to describe also the shift behavior in n. And well, in Frédéric Chissac's approach, it's very general. You have a system of relations in n and k. You compute the Grübner basis, and then you have full control about the shift in n and k. This is cool. It's very flexible, and is the right thing if you don't know how to do it otherwise. But I do a special case now, which I like. I just compute one shift in n. This is done in sigma by one shift in n. I shift once in n, and the others I shift in k. It's a kind of hook recurrence, like the Stirling number. So you shift in one parameter, and the others are on a line. Okay? But in this way, it's great because I can shift arbitrary in n and can always bring it in one step to the line without Grübner basis. So basically, I compute already a Grübner basis by ansatz. Okay? Okay, I do this, and now I insert basically the recurrence on k, which is on the line, and this hook where I can only do one shift. In doing that, I get the recurrence, and that's exactly the same recurrence that I have computed in the beginning. Okay? So let me repeat what we did here. I try telescoping. I have the shift recurrence purely in k, and I have this hook recurrence, one shift in n, and then I can bring it to the line. Pn plus 1 goes to the line equation. Okay? I try telescoping as earlier, no solution. Now I look at n plus 1. This is exactly creative telescoping. I shift in n, and now I use this relation and can rewrite that by that. So I get exactly the right-hand side. I apply now the toolbox that you have seen earlier with my higher order parameterized difference equation that I have encoded in sigma, no uncoupling. I discover no solution. So I shift twice. I apply this formula twice, first at n plus 2, reduce it to n plus 1, and then I apply it once more, and I have reduced it to the line. I get another problem, and this is just very simple rewrite rules, very efficient. I don't need any time to do that, almost no time. I get a solution, and that's exactly what you have seen in the output. Okay? Now, maybe I should mention that here already the difference ring approach enters a little bit the game, because here the coefficients actually can be in a very general difference ring setting. So I don't have to work in kx, shift of x is x plus 1, or in the q case. This works for a general difference ring or difference field. So that's good, and I have examples where you have recurrences where the coefficients depend on the harmonic numbers. So at least you can cook them up. Now, but what makes this approach for me interesting, and this is application that we can also work with inhomogeneous recurrence. So in the operator language, you always have homogeneous operators, and I focus now that the recurrence that you see has also an inhomogeneous contribution, okay? And that could be, for instance, the harmonic numbers, or more complicated objects. More precisely, they are allowed to be in my difference ring setting, so can be very complicated indefinite nested sums and products in the inhomogeneous side. And it's basically the same machinery that you see here. I look first for GS. This is this parameterized difference equation, or this higher order difference equation, and I can compute the others. I only have to say how to deal with this guy. For generality, in the input, there can be also an hs plus 1. And I have now to look also in the solution, there is this inhomogeneous contribution. If I would set this to 0, I would not know how to do it. So in the ansatz, there must be also the inhomogeneous contribution in the telescoping solution. So I have to say how, in addition, I get this gs plus 1. And that's, if you look by coefficient comparison, it's exactly this telescoping problem. So you reduce, you can solve the you compute first GS. If you have GS, you plug it in. You have given AS plus 1, and you are given HS plus 1. So it's a given summand that you have to look, and you look for the GS plus 1. And here I have the flexibility to solve in the given difference ring, or I can look for difference ring extensions to make this possible, that I find a particular solution. And of course, you can now generalize this, that you have here the parameterized version. Then it's the same thing, except that now we are working with a parameterized telescoping problem. To deal with the inhomogeneous side, I have to solve a parameterized telescoping equation, but in my difference ring that I know. So I just use my toolbox. And this is actually the trade-off. So here I cannot do anything. I just have to solve in the given difference ring, and one can show that there is no chance to look for an extension in a ring. You will not find more solutions. If you find more solutions, then actually it turns out this is not optimal recurrence, and you could reduce the order. So looking for solutions here doesn't make sense. But here, it definitely makes sense to handle with the indefinite summation problem, to look for solutions, maybe in an extension, to reduce the final recurrence order. And this is basically now the machinery that I have in hand in Sigma. We are given a sum, where the summand here is satisfies again a recurrence. So here this satisfies a recurrence relation that we try to compute first with these hook recurrences, and then I try to compute a recurrence where the right-hand sides can be R pi sigma terms, these general settings. And this works also for multi-sums. Then you have to compute more hooks in other summation variables. So if you have more hook recurrences, you can handle more summation quantifiers. This can be done recursively. Now we are ready to look at this joint work with Vadim Zudelin, and this is the conjecture that he posed. We are given two polynomials. Polynomials in T when we specialize n and m for an integer. So here you just see basically Pochhamber symbols, the alternating sign, factorials, and when you plug in n, m being integers defined like that, then you get polynomials in T. Okay? But they are symbolic, so for symbolic n and m, you have basically a parameterized version of polynomials. Here, this is also a polynomial for n and m concrete values. The sum evaluates, and then the Pochhambers here evaluate to polynomials. You get again a polynomial. And now the conjecture of Vadim was, take the derivative of the first polynomial, you keep n and m symbolic somehow, and then you sum over it, then up to the scaling factor. It's the same as you take the second polynomial twice the derivative, and then you evaluate it from 1 to infinity, that these two things agree. That looks a bit scary in the first round, right? And well, maybe you know that if you have a gamma function or a binomial coefficient, for instance n plus x over n, and you take the derivative with respect to x and then send x to 0, you get the harmonic numbers back. This has been already observed by Newton, that if you take the derivative of the gamma function in an extra parameter, you get the gamma function back times the harmonic numbers. So the harmonic numbers are again in the game. Here not so much, here even more, because you have 2 times the differentiation, so harmonic numbers of first and second kind will pop up. So, and it took a while, but then we finally got a proof. And the idea is, we show that both sides satisfies the same recurrence. And actually it's not a big recurrence, it's quite cute. So A0, A1, and A2, it's a second order recurrence. It's not big. Okay. And so I don't show you the left-hand side. It would be also interesting. I just show you the right-hand side. Okay. The right-hand side has to be split because it depends on the summand. There are there are poles, and something below a summation range is 0, and one has to be very careful. So it's better to restrict the summation ranges such that it always has finite support and it's always a non-trivial summation. Otherwise, you have big problems. So you have actually to split it into 3 parts. Also to make the case distinction that the derivative is properly defined and you get harmonic numbers as representation. So one has to do that. And let me just look at the first sum. And the first sum looks like that. If I do the derivative, it's nu goes from 1 to infinity, j goes from 0 to n, and here are the harmonic numbers involved. Harmonic numbers of second kind. This is the second page, and the third page. So it's a big guy, okay? And now I have to compute the recurrence. And the idea is now I use just creative telescoping. This sum here actually fits in my difference ring approach, poorly in the difference ring approach. So I compute a recurrence, and I compute a recurrence poorly in J, and it's inhomogeneous. So the boundaries are horrible, so if I evaluate at the upper bound minus lower bound, it's a huge inhomogeneous site. And I compute such a hook recurrence, so m plus 1, and the rest is again projected to the J line, okay? And I can do this with sigma. So I don't compute it now online, this would take too much time. Okay, here it is. So this is a sum that I insert. And then just generate recurrence. I have to do some assumptions on the boundaries that the objects are properly defined. And then here you see basically the homogeneous side, the left-hand side. It's Cj plus 1, Cj plus 2, and that's now the right-hand side that I get. Inhomogeneous. There's still an a involved, okay? So I have to send a to infinity because this was a truncated version of the sum, so I have to send a infinity. Then things simplify a little bit, but that's the right-hand side. And the objects are reduced. There are no relations among the objects as indefinite object sums in J, and the harmonic numbers are involved. So I have now a recurrence that I cannot solve. I don't find a closed form for the homogeneous version. So I need now the holonomic summation approach with inhomogeneous sites. So I compute also the hook recurrence. So I do in addition here one shift in M. So I shift once in M and the rest is on the line in J. And I get another recurrence. I send a to infinity and then I get that recurrence. Okay. And now I use these two hook recurrences, use the summation toolbox of sigma, in addition with these rewrite rules that I have shown you, and I get now this recurrence, pull in M, again with the right-hand side. And that you find here. I have to go one step further. Okay, let me go here. Okay, compute the limit. Here I define the full sum. This is basically now the double sum that I have to deal with. And I just insert the J recurrence and the recurrence once shifted in M. And it's exactly the claim. On the left-hand side, you see, it's exactly what I claim. This satisfies also from Tudelin's identity the other side. So here you have this homogeneous side. But you have also a right-hand side. There are definite sums, but only single sums involved. There are harmonic sums involved. So quite heavy. Okay. And, well, I can do it not only, and the interesting thing is I do the same thing with this sum and with that sum, and I always get the same left-hand side. But very bad right-hand sides. And then it's another round of symbolic summation to merge all these PFQs to one sum, and it turns out they collapse or they get simpler, and I get harmonic sums, so I have to apply also sigma reduce, and they all collapse to 0. So in the end, if I combine it, I get a recurrence which is homogeneous and is cute and small. Okay, and in this way, we only have to check two initial values, which is another round of summation. It's again quite complicated to do these initial values. And then we can establish basically this identity. And yeah, I pose a challenge, do this with a standard holonomic approach without dealing with inhomogeneous sites. So make all operators homogeneous and then try to do it. I think they will blow up gigantically. Would be interesting to do it, but here I think for that problem, the inhomogeneous machinery is quite the right thing. It took also a day of computations to do all this, I must say. Just computation time. Preparing the input took much longer. That's this box. But okay, this was the second part. Now I want to go to the third part. I want to show you examples from particle physics, which since I think 2008 I started a cooperation, and we constantly work, and I get always many phone calls, and we have a problem, can you solve it? And the discussions, it never stops. It's almost sometimes a nightmare, I must say, but the output is always great. So I'm not a physicist, I cannot tell you too much. The good news is there is a nice interface between what they have and the computer algebra language that I can work with, okay? So what I can tell you is these are Feynman diagrams. In this, often we do with massive Feynman diagrams in 3-loop case, where we want to describe the behavior. So particles go in with a certain momentum, particles go out with the same momentum, so it must be reflected. There is an interaction, and here in these loops, it's described what kind of interactions happens. And if you have a physical process, you actually have hundred thousands of such diagrams that you have linearly to add up to get then the information that you want, to take all the probabilities and all the situations. And if you look for such a concrete integral, there's a nice language from this graphical representation to an integral representation. And well, maybe one can say this is a Feynman integral. Very simple, in a discrete parameter n, where n comes from the Mellin space. So you either go in X space, in the physical space, or you go to the discrete space in n. Okay, it could be a bit more complicated. There might be poles in the denominator, in the Feynman diagram. They are not properly defined. So you introduce an extra epsilon in order to catch poles and something like that. This is also called the analytic space-time continuation. So you go from space-time 4 to 4 plus epsilon. So you sneak in an extra parameter to have control. And it gets a bit more complicated. Then you have also discrete parameters that you sum over. And then you have an integrand like that. Good news is, if you look at that, actually it's hyper-exponential in the integration variables, and it's hypergeometric in the discrete parameter. So you can use also the multivariate Zeilberger algorithm. There are techniques for that. We tried them with homomorphic image computations and specialized for this input. For this case, we utterly failed, so it was too big. So another option is bring it to a sum, okay? This can be, if you're lucky, a little bit simpler. If you're unlucky, which is most likely, it gets even more complicated, or it gets similar complicated. But then we have the nice toolbox that we have in hands, at least that I've shown you in the first two parts, to find nice expressions. So for instance, that integral by my colleagues from DC could write it in the following form. As I said, the integral is not properly defined in space-time 4, so you go to 4 plus epsilon, and then you're basically interested in its Laurent series expansion. And in 3-loop cases, you have basically triple pole term, and most likely, most of the time, they are interested in the constant term. And the constant term can be rewritten. You have to do, again, the derivative in some sense. So harmonic numbers pop up to do the Taylor expansion or the Laurent series expansion. And you get, again, a 6-fold sum, so no simplification. And here you have binomial coefficients, factorials, and a linear combination of harmonic sums. But now exactly the toolbox that you have seen earlier. I start with the innermost sum. I see, aha, the next summation quantifier is S, so I compute the recurrence in S. I solve in S, and do this circle and work from inside to outside with many other tricks. And in about 1 to 2 days, you get finally this result. It looks similar sized, but now it's only nice functions like the harmonic numbers of second kind. And here this is the most complicated object, such a triple sum. We have the tools to compute asymptotic expansions and all this. We have full control about that object, and this is exactly what they need. Another example, it's a 2-mass free loop Feynman integral.
So just one question.
Yeah.
So once they get this,
yeah,
what's the, how can I say, the physical semantics, or what do they do with this function after simplifying it?
Well, first they're interested what kind of functions are behind. So it's always nice for them, are theta values behind, theta 2, theta 3. Of course, in the end, everything boils down to Fortran code. And then this is attached to the CERN experiments. But they prefer to have analytic results, exact results, because you can compare with new computations, because you always compare your new results, which are more complicated, contain the previous results. So you have to compare. And if you can do this analytically, you have a big zero in the end. So it's good to have the analytic results. Also, for Fortran code, if you have that, you can now wonderfully go to high expansions and can guarantee how, up to which digits you can really compute it. You can, if you do numerical methods, Monte Carlo and others, you are much more, it's more tricky to handle things. And yeah. But this is the king discipline to find analytic results, if possible. Okay. Here, this is a 2-mass case, so we have 2 masses, not only 1 mass. In a 1-mass case, you can pull out the mass, but if 2 masses, the mass stays inside of the sum. You cannot get rid completely of it. And with Mellin-Barnes and PFQ technologies, you can, for instance, translate this diagram to 150 single sums, 1,000 double sums, 12,000 triple sums, and 1,500 quadruple sums. Here's a typical triple sum. They're not too big. Okay? And one can try to solve it. It takes about 6 hours for the sum. If you do this on a standard computer, maybe 10 years. If you parallelize it, maybe 1 year. I don't know. But interestingly enough, some of the sums I can solve. Other sums, they are hacked into sub-pieces, and they cannot be solved. Only if you combine them, you would solve them again. So hacking it in sub-pieces sometimes is not good. So what we did is, I put everything together. It takes to only 8 sums. So I merge them and their structure, so you can bring them together to some similar summands which are similar as a hypergeometric term. You can merge nicely together. And then the idea is to tackle these huge sums. Then basically the idea is I put things together, and then there is bigger hope that I can solve it, and I have less sums. Instead of 20,000 sums, I have only 8 sums. The problem is, for instance, this quadruple sum here has now a summand of size 266 megabytes, so it's big. And the triple sums, there is about 1 gigabyte size, so quite big. But I managed to work from inside to outside with my difference ring theory, and in the end I had variables of 500 variables, so it was a huge difference ring extension, but I made it, okay? So I got here 1,000 sums, 700 sums, and in the end I add up everything together. You get an expression which was still big, 154 megabytes with 4,000 sums, but they have relations among them. So I applied sigma reduce in a smart way, tried to find all relations among the sums. One of them looks, for instance, like this. It's a sum of a sum of a sum. Here's another sum, here's another sum, and then you sum over this. This is basically, you could, by shuffle relations, you would get a 1, 2, 3, 4, 5, a 6-fold sum, indefinite necessity. So there are quite some things. And it took about 32 days to find all relations, and then the whole expression collapsed to 8.3 megabytes and only 74 sums. No relations anymore amongst them. And this is exactly what the people in physics needed and wanted. Okay. Recently, we've not worked only with sum and integral representations, but we also worked with coupled systems. You have seen today in the morning a coupled system, and they're huge. This can be maybe 1,000 times 1,000 system. But the nice thing is they rely on each other. You have a little system in the beginning, and then you have a next system which is not too big, which depends on the previous system. So you solve first this, and then you come to the next one. And the smaller systems are maybe 12 by 12 or 15 by 15. Still not easy to handle, but better. So the idea is to uncouple it and to solve. But this is also expensive solving. And sometimes the master integrals, again, hack these systems and you don't find solutions. Whereas, you know, in the final result there is a solution, but these sub-problems don't have solutions, only in the combination. So what I did here is, what we used recently is the guess and solve technique. So we start with such a coupled system, uncouple it, go via holonomic closure properties to the corresponding recurrence. You have seen this also in talks before, that you, by coefficient comparison, a differential equation can be turned to a recurrence for the coefficients. And then, using the recurrence in a recursive way, compute 10,000 values. This takes also time. This can be very, very big, and this takes the most of the time, maybe 2 months to compute this 10,000 values. But now, having these values, you can do numerics if you want. But more interestingly, you can guess a recurrence. So recently we use always the Euler algebra in Sage, introduced by Manuel and others. Guess a recurrence. Then one can do asymptotics. There are asymptotic tools on the recurrence level. One can do the solving part. This is what I'm most interested in. Solve the recurrence. Or solve it partially, and you get an operator which cannot be solved where maybe PFQs are behind. This is also interesting. And recently we also go to the differential side and then do analytic continuation of huge recurrences. This is what Mark often is doing. So this is also useful. I want to show you just one example here. This path, having the moments, getting a recurrence, solving it. And here's a simple, I don't show you how to compute the initial values. These are the first initial values. These are rational numbers. And you see they grow. So if you go to the 1,000th term, these are gigantic numbers. Okay? Then we solve it with Sage. And I don't show you now the code. Here is the recurrence that we can guess. This is the first coefficient of Pn plus 1, Pn plus 2, Pn plus 3, 4, and 5. It's a recurrence of order 5. And this is a minimal recurrence which describes the physical problem. Okay, we guessed it. This, at least, is my claim. There is no shorter recurrence. Because you do several recurrences, you compute the GCD, and then it's very likely that that's a minimal recurrence. Next, we solve it. We use sigma. And you find, well, 5 linearly independent solutions. First one, second one, third, fourth, and the fifth one. This is exactly what I have shown you in part 1 and part 2. And the most complicated object is that. So just by a rational number arithmetic, we obtain the final result in physics. And taking the first 5 initial values, this is the closed form. And this is interesting. If you want, of course, you can produce again the sequence and maybe more. So maybe we need 1,000 for guessing. I have 3,000 in hand, so I check that they agree with 3,000 values. So it's very likely that it's correct. It's not a proof, I agree, but the physics people are extremely happy. So I know sometimes they only compute 3 more values than they have what they use, and then they verify the next 3 values are correct, and then they're already satisfied. So if I can compute 2,000 more values and say they are still fine, this is much more likely, okay? And the recurrence that you have seen is a minimal recurrence to that expression. So that's a much more compact way. So sometimes indefinite nested sums are much better than if you would compute the minimal operator describing that, okay? And working with that is more efficient. And yeah, afterwards you can rewrite it with harmonic sums. These are special tools to the harmonic numbers and these iterative integrals. It's the language that the physics people like more. And as you have seen earlier, you can compute also asymptotic expansions. We have now everything under control. We get from rational numbers the asymptotics together with all the constants. We don't have to hunt numerically and by PSLQ for constants. We get them automatically. That's a cool machinery. So, which we use heavily. And let me just show you another example. So here are the packages that we have worked on for making this machinery possible. And let me show you, and this was the largest recurrence, one of the larger ones, let's say, that I managed to solve, really solve. It's a recurrence of order 44. The polynomials have degree about 1200, and one typical digit is about that. Okay. So I am, just for fun, here's the recurrence. These are the first polynomials. So you see, I don't stop, it's 25,000 pages. I print it out, so it takes, the PDF file is 150 megabytes in size. So yeah, don't print it. And yeah, here's a closed form. Here you see the binomial coefficients. There are binomial sums involved with 2n over n as letters. There are the harmonic numbers involved. And that's it. It's in total, how many pages? 10 pages or 9 pages. So this line I don't count here. So 9 pages. And the recurrence was a minimal recurrence. So 10 pages versus 20,000 pages. So you see there's a dramatic simplification going on and compact representations. Okay. Okay, now let's go back. Yeah, and using these tools, so symbolic summation, also symbolic integration, we have tools that we worked, this coupled systems, solving recurrences, but also the guessing and solve approach. This makes it hopefully soon possible. Since 15 years we are working on a project where things are needed for CERN and for other experiments. We are close to provide the Fortran code now based on our symbolic expressions. And we are currently trying to go to for loop. It's much tougher to do that. It's dramatic difference. But we try the first things also there. So I hope to convince you that symbolic summation, solving recurrences, and all this is useful in applications. And I would be happy if you use the tools, and if you have questions how to use it, or please send me an email. I'm always happy to answer questions. Thanks for your time. Just in time, ready for coffee.
Thank you. I'm not sure how to make these work, so let's take questions.
Concerning this P of Qs, how large are the P's and the Q's in the hypergeometrics? Like,
so there are P of Qs inside, and they are mostly modular functions. So they are not too complicated, at least what we have identified. So there are simpler cases where we have coupled systems. When we uncouple it, we see the first building blocks quite below of the coupled system are these elliptic functions. And based on that, you have iterative sums or integrals on top. And here we have control. In other cases, so I guessed sometimes a recurrence where we cannot solve it. I fail to solve the recurrence. It's of order 40 or something like that. Then we do analytic continuations as a way out of it, having the differential equation and the recurrence. But I managed to factor off, let's say, 30 factors, and then I get as leftover a differential operator or recurrence of order 10. And I have no idea what solution is behind. Maybe there are some P of Qs in linear combinations. Maybe there's appel functions and something more complicated behind, and maybe something even worse. So I don't know. And this is the more recently in particle physics, one enters physical problems where the world gets more and more crazy, let's say. And one needs other tools or combined tools to make it possible.
So obviously you have crazy big equations here. It's really an impressive scale, but how are you able to then validate that the result that you got is actually a correct one? Because for example, you had a series that you said that only to evaluate it would require 10 years.
Well, if you have a coupled system, we know it's holonomic, so the solutions are holonomic functions. One can bound things, I guess, and say how high can be the order of the differential equation by going recursively up. Because if you uncouple m times m differential system, you get a differential equation of order m for the scalar case. So there might be things, but it will be high. And if you know the order, then you can do something by that. But I think it's not worthwhile to do it. It was hard enough to get the result, and we are confident that it's correct, and the physics people are happy with that. I don't waste time for that. Yeah, this is somehow more experimental math in this case. For smaller cases, I'm very interested, but for these big ones, I don't dare to do it.
Yes, so you mentioned quite often that, okay, the computation was taking 1 day, but it was on what type of computer? PC, cluster, and also what is the amount of memory which is needed?
I think this sum that you have seen, the six-fold sum that I showed in physics in the beginning, this can be done with my notebook in 2 or 3 days. So these other things where I solve the recurrence, these big ones, and this runs for 4 weeks. I don't use my notebook. I use it for something else. So we have computers, and in particular to get the moments in the moment I compute 25,000 coefficients for coupled systems for guessing in the moment. This runs maybe in total 1 year on maybe 8 machines, and the biggest machine has 2 terabytes. The smaller ones have maybe only 1 terabyte. So we need memory to do that, and we need the resources, and one uses also the kernels, and I parallelized a lot. It worked great, but suddenly for these big problems I said no, parallelization is not good because each kernel needed too much memory, and it's better to linearize it again, and it's better to run things in parallel, several such problems, than parallelizing one problem, because suddenly the memory explodes. If you have 10 kernels and each kernel needs maybe 200 megabytes, it's not big, but if you take 10, suddenly you have the 2 terabyte, and it's getting a disaster after a while. So sometimes linearization is again good if you have huge data.
I have a question. So at some point you said once I've solved everything, I can do the asymptotics in n.
Yeah.
So could you obtain the asymptotics without solving everything?
How is it working? So there are different ways. One approach is you always go to the. So one of the main tricks is so you have your function here, and then you go to something like that, to the Mellin. In physics, they like it in this range very often. And then you use this function to manipulate to integration by parts and other techniques. You use Watson's lemma and others to carry things over, and then you get the asymptotic expansion. And the good thing is these functions, you get constants, which are again integrals, which are constants, and these constants are then the theta values or something. So doing it in this way, you get the asymptotic expansion plus the constants in symbolic form, where you can do numerical evaluations. If you don't know which, by PSLQ, you can hunt for it, or you can get them explicitly for a database. So harmonic polylogarithms and harmonic sums are related to each other, and then also the multiple theta values are related to these iterative integrals at constants, and you have a dictionary to go from one word to the other. But the key is we go to the integral representation, which looks much more ugly than that, but it's more useful for asymptotic expansions. And we need basically theorems to justify that this is correct. So for the theorems for correctness of the rewrite rules, we have analysis in the background. But once this is verified, we can use the computer algebra methods without thinking.
Any other question? Well, let's thank Carsten again for the 3 lectures.